Welcome everybody. So it's a pleasure for me to introduce you a little bit to the potential of spectral photon counting detectors. And I'll first talk a little bit about the basics and the physics behind that. And I'll show you the current state of the art in the clinics. That's dual energy CT, which is heavily used today already. And then of course I'll show a few examples, literature review of the things that are presently pursued in terms of spectral photon counting for future. Now, CT is about reconstructing slices, the CT volume from the projections that you're recording. And from a physics point of view, we are essentially after the attenuation coefficient, the 3D distribution of this attenuation coefficient in the body. Now, if you look closely at this attenuation coefficient, you obviously know that there is the photoelectric effect, where a photon comes in, kicks out typically a KH electron, and then you get absorption by that, or you have Compton scattering, which creates attenuation in the body through the interaction with the photon. And that's an interaction with a loosely bound electron on the outer side of the atom. Now, if you look into the energy dependencies of these two basic effects, you actually see that they are quite different. So the Compton scattering, this is a double log plot, is relatively constant or has a smooth energy variation, whereas the photo effect actually has a quite dramatic e⁻³ decay. And most importantly, it changes from one material to the other. If you compare here the Compton effect, you see it's relatively similar for the two materials, but the photo effect actually shifts to the right. So if we model that by a little equation, we would write that the basic attenuation coefficient is the photo effect, a coefficient of that, and the Compton scattering. Now, if you look at these two energies and the two plots, you can actually tell the difference because if you take one energy here, one energy here, there's a small difference, for example, in aluminum and a large difference for iron. So that means that by measuring two energies, we can actually extract the ratio of the photo and the Compton coefficients and tell the difference of different materials. So we can be energy and material specific by measuring two different energies. Of course, if you look closely, you also see that there's additional features in the photo effect, for example, the edges. If we also want to use these edges to discern between different materials, obviously we have to measure even a third energy to get more information on the samples. Now, before I start talking about measuring three energies, for example, photon counting detectors, let's look at the state of the art, which is dual energy, so measuring two energies in the clinics already. Different vendors have actually developed different approaches. There's, for example, a dual KVP switch system by GE that actually modulates the KV, the acceleration voltage, while rotating the gantry. And in that way, you get access to two different energies. There's another system by Siemens that uses two detectors and two sources, and in that way you can configure one at one energy and the other one at the other energy and get two energy bins in your measurement on the image. And then finally Philips came out with a spectral separation on the detector by actually putting two layers on top of each other. So the first layer would take more the lower energies and the lower layer takes the higher energies. So in that way you also get two energy bins. And these systems are actually in daily use today in most of the big university clinics. And what you get from that is, of course, by summing up all the energies, you can get a conventional image. That's, for example, an abdominal scan. And from those two energy bins, you can now process, as I explained before, the Compton effect and the photo effect. That's not typically displayed, but what is displayed is usually a so-called virtual non-contrast image and the iodine material density. So this is basically just a different set of basis materials where you have now used these two dual energy measurements to calculate an image that has no contrast agent and one that actually has only, for example, the iodine contrast agent. You can also use these duality information to calculate other derived images. You can, for example, compose so-called virtual monochromatic energy images. So, and this is a fusion where you have scaled the photocompton effect contributions to a relatively low energy at 40 kV, which actually enhances the soft tissue contrast by using the energies that are quite low. Another thing you can also do, if you look at the ratio, you can actually come up with images that map the C effective. So that's the average atomic number for every voxel. This is also something you can get from the ratio of photo to compton effect. This is in daily use in the clinics today, and I give you a few examples what that is actually useful for in clinical routine. This is 2 patients after an interventional thrombectomy. So this is an interventional procedure in the brain. And typically after 10 or 12 hours, you do a control scan because you want to know if there are some hyperdense areas left, which would show if the operation has been successful or not, so if you have still bleeding or not. And you see in these 2 patients here that there's an hyperdense area here and here. So the big question now is that actually new blood, hemorrhage, or is it a remainder of the interventional procedure where iodine has been used? And if you look now in the virtual unenhanced image, you actually see here that there's a hyperdense area. That means there's blood in this patient, there's no blood, but you see a signal in the iodine image. So there you can be sure there was an iodine still left from the interventional procedure. And here it's actually a bleeding that you have to cure. This is actually backed up by an MR measurement afterwards. So these 2 features can help you to discern between hemorrhage and iodine, which is actually quite good. That's another case here, which is quite interesting too. That's a conventional 120 kVp scan, again of such a patient, and you almost see no variation. If you now do the material separation, take out the iodine, and look at the virtual non-contrast image, which should only show the soft tissue and the bone here, you actually see a hyperdense brain tissue here. And that's a sign of an infarct, so you can actually be more precise about detecting infarcts with dual energy today. Now that's another example that now highlights, for example, the usage of these mono-E images where you get more soft tissue contrast by scaling down the measured real images to lower energies. And if you look closely, it's actually a patient that has some metastasis from a renal cell carcinoma. You might be able to pick up this one here, which is actually very clear in the mono-E image. And if you zoom in, you actually see that here's another lesion or another metastasis here, which you would actually not be able to pick up in this image. So these are cases where dual energy actually really plays a role in the clinics today. That's another thing that shows the usage of C effective. It's a patient with an ileus. So the smaller bowel is actually blocked and filled with liquid. And the task of the radiologist here is to figure out where the obstacle is in the bowel. You see it? It's actually very difficult. You can't tell from that image. If you switch here, you see it very clearly. So there's something here. It's a gallstone, and that actually blocks the bowel in that patient. And you can also tell that this is a lipid-rich gallstone because it actually has the same C effective as the fatty tissue around here, and that is actually quite helpful because then you know what the problem was. Okay, now more than 2 energies. So this is what's coming up. You have seen that dual energies or using 2 energies is already quite effective in clinical use. Now, if you want to move beyond that, you have to actually change the approach, because doing this KVP switch using 2 layers or 2 sources, you can't really cram another source and detector in the gantry. So you actually switch detector technology to photon counting. Photon counting has been explained in detail yesterday by Krista. I just summarized that here quickly. So essentially, you have the photon that goes into a direct conversion sensor layer. You create your 2 electron hole pairs, and then you pass it directly through a bump bond onto an electronic circuit that can now sort those photons according to energy and with several thresholds into different energy bins. So now it looks that the equation is missing here. I'm sorry. So what you should see here is actually that with this additional information of 4 bins instead of 2 now, we can not only compute the Compton parameter and the photoparameter, but we can also compute now additional coefficients for the different edges of different materials. So we can, for example, with 4 bins, obviously also extract 4 different materials. So if we have 2 input parameters, 2 materials can be computed as a rule of thumb, and if we have 4, we can actually do more with that. Now, the approach would then be, and this is one of the first experimental demonstrations on a preclinical system done by Schlomka et al., it's actually from Philips here. You would then measure the sinograms or projections at the number of bins you have available in your system, and then you calculate the photo effect from that, the Compton effect, and for example also the KH contribution of gadolinium if you have used that as a contrast agent, or iodine, for example. And with this you can now create material-specific images, now more than the 2 that I showed before, because you had more input bins to start with, and you have a gadolinium and, for example, an iodine image in the detector. Good, this has actually been investigated by several preclinical scanners that have been built over the course of the last few years. That is one suggestion that is actually about CT-based colonography. You know, colonoscopy is usually an interventional procedure where you actually insert an endoscope. That's not actually very comfortable, so you can also do a CT-based colonography screening, and that basically means that you give the patient some contrast agent to drink, and if this would now be the bowel, you see that this contrast agent actually enhances the inner part. Now the question now is, if you take that out, if you actually see some polyps here on the side, and these are mimicked in a phantom experiment here with a polyp that is actually also contrast enhancing, or some that is not contrast enhancing, and the ones that are not contrast enhancing would just be cysts that are not pathologic, so they can stay in there. But if you would actually see something that is also enhancing after an IV injection of contrast agent, that would be a problem. In this case, that has been mimicked by actually injecting gadolinium intravenously, and you see that now in that image popping up, whereas the inner filling is just the one from the iodine that has been swallowed. So in this case, you could do a single scan for discerning 2 different contrast materials, and also a native image, which would be one of the potential applications. Other applications that have been investigated are connected to something that is called multiphase CT. What is multiphase CT? So actually in clinics, very often one gives a contrast injections. And now if you, for example, have a tumor or lesions in the liver or any other organ, this contrast is distributed in the body, first in a so-called arterial phase, so that's the first blood flow through the system, and then later, if it goes through the heart and comes back through the liver, it has another so-called circle, it's a portal venous phase. And by doing now scans, CT scans at different times, you can look how different lesions take up the contrast agent early or late, and this actually gives you a diagnostic information of whether it's a benign or a malignant lesion. It's used all over the body, and it's quite something that is very important. Now with photon counting, you could now imagine that you simplify this scheme so you don't have to do repetitive scans. So what you actually do is you take one contrast agent, you inject at one time, you get it through the arterial phase, you wait, and then you inject the second contrast agent, such that at some point you have basically a portal venous phase or a late phase from the first contrast agent, and you have the arterial phase of the second contrast injection, and then you do one spectral CT scan. So you have basically replaced 3 scans, a native scan before, one scan at time point 1 and another scan at time point 2 by one single spectral CT scan, which can now give you the native scan, this contrast agent, and probably also the other contrast agent. That has been investigated in a couple of publications. This is an early simulation experiment where this was done or demonstrated in silico on liver lesions, and you see Here's the integrated CT image of metastasis in the liver and some hemangioma, which is actually not pathologic. And they actually have a different sign. The hemangioma typically starts with some little contrast uptake in the outer areas and some filling in the later stages of the contrast agent distribution, and the metastasis presents with a rim both in the earlier stages and the later stages. So you could get that at one shot. This has been demonstrated actually in vivo on a system that has been built by Siemens in this case, and that's one of the first results that have been published by Siemens et al. Last year, which basically show these different timescales and contrast uptake in the kidney. So here you have the kidney. You see there's a lot of intensity in the grayscale images, so there's a lot of contrast agent in there. And now you see that, for example, gadolinium was injected first, so you get a rather smooth distribution and late uptake here in the gadolinium image. And in the iodine image, you see from the aorta that you have actually, you are in the early phase and you see some uptake on the edges. In this case, one could also separate a bismuth map where there's nothing in there and calcium. So you see with one scan, you can differentiate and get the different phases for different organs, which could be quite interesting in the clinics. Here's another example, that's about cardiac CT. Cardiac CT, you are using these phases to look at signs of infarct. If you actually have a late uptake in a later stage phase, like shown here, then you can actually be sure that there's a problem. Here it has been, let's go back, here has been used iodine and gadolinium, and then again in the procedure I just explained you in the multi-phase problem. So these phases are something that I use quite often. This is a recent result from the Philips preclinical system. Colonography et al. It was published also last year, where they have actually experimented with different contrast agents and the timing of them. So those show different scans taken subsequently after different timescales. And here you have gold. It's an experimental contrast agent. It's actually a blood pool contrast agent. That means that it does not wash out as quick as, for example, iodine or gadolinium. You see the iodine that's injected here actually floods very quickly and then actually washes out also after a relatively fast timescale, whereas the gold is more or less staying in the body and is distributed. Again, you could now use this information that is taken in one shot with a spectral scanner to look at the different pharmacokinetics of different contrast agents which are presently under development. So I think that's also kind of a nice application. Now, then finally, if we just leave these colored images away from for a second, then people have also investigated simply the fact that these photon counting detectors come with a higher resolution. Because the pixels are typically small, you can now, for example, think about visualizing stents as done here in this prototypical experiment much better than in a normal system. So that's actually a Siemens dual source, dual detector system. That's the photon counting detector results with high resolution. And that's the normal imaging system. And you clearly show that in here, if you push it to the limits, you can actually get higher resolution. That, of course, is sometimes not easily to couple with the energy resolution, because for the energy resolution you need a charge sharing compensation, and in that case it's probably not ideal to combine. Okay, a few words finally about our experience with the X-counter or direct conversion detectors. Since I'm talking here at the stand, we have in Munich actually two systems, benchtop systems where we do basically rotating CT experiments and try different detectors. So we're using a Flight X1, the Tor FX7, FX10, and we also have a rotating gantry small animal experiment, which is presently equipped with a Hydra system. Both can go up to 160 kVp. So, of course, we first demonstrated of phantom samples that all that what I've been telling you for the material separation works. For example, it's a little phantom here. It's the integrated conventional scan And this can be separated into the iodine material density. So these two vials actually contain iodine, and this is the virtual non-contrast, so separated after photocompton material separation into iodine density and virtual non-contrast. So this is just reproducing the photon counting results as what you have today in clinical use. We also looked at some biomedical sample. This is actually a human hand ex vivo, and of course conventional radiograph, and you can process now, as I said, with the dual energy information from the photon counting detector, the Compton, the photo effect, that you can convert into the different basis materials, soft tissue and bone. So now you have actually the bone completely separated and the soft tissue. And if you look closely, for example, you see little pieces of bone here or fragments down here. That is actually much better displayed than in the normal image. So here you get a pure bone image, and you might actually have access to microfractures more easily than in the standard radiographic images. So I think also besides CT, you can have quite a few applications of these detectors. Now you can be creative about how to present that to radiologists, or in an overlay, or in different ways. Yeah. Of course, you can also process from these two photocompton contributions these so-called mono-E images by fusing and extrapolating these contributions to 40, 80, 120 kVp. And what you basically see here, that at lower energies, obviously the photo effect dominates. That's the steep curving rising at the lower energies, and for higher energies it more pronounces the Compton effect, which is essentially the soft tissue. So also works for CT. This is a human knee, also ex vivo. The integrated scan, we do the whole procedure, Compton, photo effect, discrimination, separation, we convert that to soft tissue and bone. Now you have the pure bone mineral, or the pure bone on this right hand side, and here you see obviously that it highlights the soft tissue that is essentially around this bone, and that might be helpful for cartilage detection, and can now be creative about the overlay in one way or the other. Or you can also calculate this effective C map that I showed you before, which gives you now access directly to the average atomic number that is present in the different energy bits, or different parts of the image. That was actually reconstructed with a dictionary-denounced model-based iterative CT reconstruction, which is actually state-of-the-art. Good. With that, I am almost done. I'd just like to show you also that, as mentioned before, you get all that plus for free the high resolution. In this case, the detector has 100 microns, so you see easily the individual bone trabecular, which is quite useful. For example, if you calculate fracture risk for osteoporosis prediction, but this is something, some flexibility you actually have in these photon counting detectors. Finally, that's a very recent result where we try to get even more energy bins, in this case by doing a fast threshold sweeping, which the detector can do. So we have about 48 thresholds theoretically, and then we can actually, together coupled with charge sharing correction, do almost as many different materials as we want. Here it's see, this is a gadolinium foil. You have gold here, you have tungsten here, and then you can of course color it in your different ways. So in this way you could get access to as many K edges as you wanted, but limited is of course how many contrast agents you can inject into the patient, and how many you get approved in the end. Good, with that, thank you for your attention, and thank you for being here today.